Section 3.2 Nonlinear Models. We will look at the population models and chemical reactions in this section. For the population models, in the ideal situation, the population grows exponentially, or we get the differential equation as dp dt equals k times p, where k is greater than 0 and k is the constant or called the growth rate. A new assumption, dp dt equals p times the function of the p. For example, the logistic equation, dp dt equals p times the quantity A minus B times P. Let's consider this example. For the animal population P of T, the model is dp dt equals 0.0004 P times 150 minus P, where P is 0 equals 60. Part A, use the phase portrait concept to sketch representative solution curves. Part B, solve for P at T. And Part C, what happens to the population in the long term. As you see the right-hand side of the differential equation, they are involving just the dependent variable P. So this is the autonomous equation. So we can sketch the phase portrait. First of all, find the critical value. Which can be found by letting dp dt be 0. So we solve for P, where 0.004 P times 150 minus P equals 0. We get P equals 0 and P equals 150. Draw the vertical line, locate P equals 0 and P equals 150 on the vertical line. Identify the arrow, whether it's going up or coming down, to represent the derivative dp dt greater than 0 or less than 0, respectively. For the p is greater than 150, dp dt is negative, so the arrow is coming down. For p between 0 and 150, the dp dt is positive, so we have the arrow going up. For the value of p less than 0, we have the negative side of the dp dt, so the arrow goes down. This tells you P at 150 is stable. P at 0 is unstable. Sketch the solution curve. As P at 0 is greater than 150, the solution curve approaches the line P equals 150. For P subscript 0, anywhere between 0 and 150, the solution curve is increasing and approaching the line P equals 150. For P subscript 0 or the initial population less than 0, we get the solution curve, decreasing curve, and go away further away from the line P equals 0. Next, part B, we're going to solve for P of T. This is the separable equation. So we're going to separate the P and dP, T and dt. Then we get 1 over P times 150 minus P times dP equals 0.0004 times dt. Integrate both sides. The left-hand side, we use the partial fraction technique to get the fraction with the denominator P and the fraction with the denominator 150 minus P with respect to P equals the right-hand side, which is 0.0004 times T plus C. The numerator of the first fraction is 1 over 150. The second one is 1 over 150 as well. So we take 1 over 150 out as a common factor, and the antiderivative of 1 over P is natural log P. The antiderivative of 1 over 150 minus p is minus sign natural log quantity 150 minus p equals 0.0004 t plus c. Multiply both sides by 150 and combine two logs as the quotient form. We get natural log of p divided by 150 minus p equals 150 multiplied by 0.0004 to get 0.06 t and then plus C1 where C1 is 150 times C. Now we are going to use the initial condition, which is when t equals 0, p equals 60 to find C or C1. Before we substitute the number, let's raise the general solution there as the power of the e to get p over 150 minus p equals e to the power 0.06 t plus c1, or we can rewrite it as c2 e to the 0.06 t. So p over 150 minus p equals c2 e to the power 0.06 t. As t equals 0, p equals 60. So 60 divided by 150 minus 60 equals C2 times 1 or just C2. Therefore, C2 equals 60 divided by 90 or 2 over 3. So we get P over 150 minus P equals 2 over 3 e to the power 0.06 t. Multiply both sides by 150 minus P. So P equals 2 over 3 quantity 150 minus P times e to the power 0.06 t. Simplify the terms. Multiply all by 3. So 3 times p equals, distribute 2 in there to get 300 times e to the 0.06 t minus 2 times p times e to the 0.06 t. Collect the terms involving p to get 3p plus 2p e to the 0.06 t equals 300 times e to the 0.06 t. Factor p out to get 3 plus 2 times e to the 0.06 t equals 300 e to the 0.06 t. So we get p as a solution for p equals 300 times e to the 0.06 t divided by 3 plus 2 times e to the 0.06 t as a solution for part B. And then in part C, in the long run, that means as t approaches infinity, what happens to the p? So we take the limit of the p as t approaches infinity, or take the limit of 300 times e to the 0.06t divided by 3 plus 2 times e to the 0.06t as t approaches infinity, which will give us 150.